Hi, everyone, and welcome to day 4 of our summer school is on AI for buildings and cities. I'm glad to be here um, to introduce you to day 4. Climate Change AI is organizing this summer school. It's a global nonprofit that catalyzes impactful work at the intersection of climate change and machine learning. You can find out more about Climate Change AI at our website, climatechange.ai, and also on the platform. Sign up to our newsletter and follow us on social media platforms, looking up Climate Change AI. For today's session, you can ask questions on our community platform. Make sure you sign up to that and use the lecture Q&A channel on the community platform. And given the high number of participants, not all questions will be asked by our guest lecturer today, but the ones with upvotes will have a higher chance of being asked. So stay active out there and to get your question answered. So our schedule for today, we have our guest speaker, Marcus Voss, who will be giving the lecture for the next 90 minutes or so. And there might be a short break, but we'll play it by ear as Marcus runs us through this awesome lecture that he's prepared for us. And we have myself, Samuel Fernandez, and Dan Lin Hu, guest lecturers, guest TAs today, and our speaker, Marcus Voss. So without further ado, I'm going to introduce our speaker, Marcus Voss. Marcus is an AI expert at Birds on Mars, where he's responsible for AI applications for environmental sustainability. He's also a member of the board of directors at Climate Change AI and has been a lecturer on AI and data science at many different universities. We are really honored and glad to have him here today to lecture us at the summer school. And he's involved in many awesome projects. He brings in real-world experience into today's session. So without further ado, I hand over to Marcus. Marcus, take it away. Thank you.
Marcus, you're muted.
Classic. That should have. Yeah, thanks for tuning in and being there. And yes, so this, thanks for the interest in AI for buildings and cities. Just a heads up, this talk is focused on buildings and cities, and the title is chosen because of this was the section title of the Tackling Climate Change and AI paper that was introduced in the first lecture. But I'm going to talk more about buildings today. I mean, I have 2 or 3 applications which are also a little bit around cities and not so much focused on buildings. But most of what I talk today is going to be buildings, because if you think about cities and how cities are affected by climate change and how cities affect climate change, you're going to notice also there's, of course, the transport sector, maybe industry, even depending on the city. And there's whole separate lectures on each of these topics. So today I'm going to focus mostly on buildings. Just briefly, I mean, I've been introduced already. But just briefly, like I said, I work for a small consultancy right now, where I work on sustainability projects. I'm with Climate Change AI, and before that, and this is actually where I have my research background on those topics that I mostly talk about today, and where I also have a few of my research work that I've done at that time, but also after that is when I worked at TU Berlin. Here you see me actually, it's quite close in my neighborhood on the Gasometer, which is in Schöneberg, where you see those small wind turbines. And back then we had a lot of data of like a intelligent district of wind turbines, solar panels, batteries, electric vehicle charging stations. And we could do a lot of these forecasting and optimization topics that I'm also going to talk about today. So just to give you that background. What I'm doing today, maybe one topic that I didn't fit so well into the lecture slide, but it's still pretty cool, and it went live to be tried out by the Deutsche Bahn, so the train company of Germany. There we actually work on the glyphosate phase out and giving decision support to the vegetation management. And I worked in a project team where we used segmentation models to detect vegetation in the train tracks. So I mean, here you see you're in the city, so you could even connect it to today's topics, but that's one of the cool projects that I've been recently working on. But yeah, let's talk about buildings. Why are we talking about buildings today? And I think this is maybe the first opportunity already to get you into the picture. Just your very first initial thoughts, like how do buildings affect climate change? I'm going to hand over to Samuel for that. So there should be a Google form link that you should be able to submit some short answers, like just your initial thoughts. How do you think that buildings affect climate change before we dive into that? Yeah.
Thanks, Marcus. I'll share in a second here. As soon as I get some responses.
Are some answers coming in?
Just got the first one. Just waiting for a few more, and I'll share my screen.
I mean, really, it's no wrong and false. I'm going to share with you some energy consumption, heating, negatively. Yeah, we will see about that, but definitely also negatively. More energy use, creating heat islands. Yeah, so this is then more to about urban planning. So like thinking of the whole city. Cooling. So I assume this means energy used for cooling, heating and cooling of the building, the steel and the cement material. That is already very good. Construction of buildings. Yeah, so we kind of see there's energy consumption, heating, cooling, and steel and cement. Pretty good. Energy efficiency. 40% of global greenhouse gas emissions. That's, I think, a little bit high, that number. That would be interesting where you got that from. We're going to see a little bit different ones. Yeah, but in general, I think there's a lot of good things. We've seen waste, toxic gases. That's also good. Yeah. I think that's a good start for the discussion. Yeah, so let's go maybe to this slide. Maybe you've seen this or a version of that institute. It's a little bit old, but generally those sort of numbers are still in the right ballpark. So if you look at where greenhouse gas emissions are coming from, and we think about buildings, then yeah, the obvious ones are some that have been mentioned before, and we're going to deep dive a little bit into those numbers. But so there's residential buildings, commercial buildings, which use electricity and heat. So you can kind of see that coming from the left side of that Sankey diagram. So that's basically what we've seen. Then there's iron and steel. I highlighted only part of that because iron and steel, of course, also used for non-buildings. But definitely parts of that iron and steel is going to be used in buildings. Then there's cement. We also had that in there. So that's definitely also a point. If we're then thinking about cities, so beyond buildings, then definitely, like I mentioned, some of the industry could be accounted for cities. Then there's, I highlighted some of the transportation also, because not all transportation is in cities, but a lot of transportation is in cities. I mean, not so much of the flight, I guess, hopefully. I mean, some people are trying that. But yeah, definitely some of these activities are then causing greenhouse gas emissions. So that's definitely on the mitigation side where we have to address some of these emissions. So this is also, if you then look into the climate, into the IPCC reports and look into the mitigation strategies, you're going to see that if you look across all these scenarios and all these actions that you can take, you're then going to find that also in order to get to net zero greenhouse gas emissions, you can kind of see, okay, what are the contributions by sectors that need to be done to achieve these greenhouse gas emissions. You're going to see that buildings, proportionally to what we've just seen, play some roles, right? So here's a distinction between direct and indirect emissions. We're going to talk about this in a second, but generally you see that it's a considerable part. So it definitely makes sense for us to talk about also buildings in the context of climate change today. But this is just the motivation for now. Also, another really cool, bigger picture image that I like is this one from the IPCC reports. It's from the summary of policymakers, where they, on the one axis, they have the greenhouse, the potential contribution to net emissions. So basically what we've just seen on the other slide. And so here you can see that buildings compared to others, and you don't have to look at the specific the specifics here right now, but you can kind of see that compared to the others, it's not as much as, for example, in the energy sector, but of course, some of the energy goes into buildings. It's not as much as, for example, in the agriculture and land use. But what you see is that they also highlighted the costs here. So especially if you look at transport and buildings, you see that there's a lot of blue bars, blue meaning that the costs are pretty low compared to a lot of other measures. For example, here the dark red, which are rather expensive. And also for energy, for example, you have a lot of blue because it's very cheap measures that you can take before it gets really expensive. So that's why, like, if you look at buildings, which partly play a role in the energy sector and partly here on its own, you can kind of see that generally you have some really quick wins or low-hanging fruits that you can focus on. That's why I kind of also see buildings as an interesting area to talk about in the context of climate change. Okay, so this was the very basic high-level introduction, but we're going to deep dive into this a little bit more now in the second part. And I'm going to tell you a little bit more about buildings, how they generally work right now, and where machine learning can fit into this picture in the second part now. And then in the third part, we're going to give an overview of different and examples of different applications of AI and machine learning in this sector. In the end, I'm going to give you some research topics that you could be working on, maybe some research directions, and have some final concluding remarks. And then we have some time for discussion. Okay, let's talk a little bit more. Let's deep dive a little bit more into this bigger picture that we've just seen. So we just seen on this figure before that there's the distinction between indirect emissions and direct emissions. So the indirect emissions is everything that's happening offsite from the building. So that's, for example, let's take this building here. I get energy in two different ways. One is the heating, which is provided by warm water, which is heated by gas in this building, unfortunately. And then there's electric power, which I get provided to this building. And electric power is generated here offsite. It's generated in some power plant in Berlin, whereas the heating is provided on-site. So it's gas that's burned within the area of this building. So this would be then direct emissions to heat this building. This may not always be the case, right? So there's other buildings where, especially also in Berlin, where the heating may be offsite somewhere, and then just the hot water is transported to the building. But here in this case, it's on-site. And so this is where you have the distinction between direct emissions and the indirect emissions. And also, for example, this building had a solar panel on top, or had something like this could also be that there's direct production of renewable resources here, which of course then wouldn't have some, I mean, you could debate if it has emissions or not, similar, but for example, in Germany, something that has been popular in the last years were combined heat and power plants. And if you have these combined heat and power plants, you may also have on-site production of energy. And then, as you already figured out yourself, when in the question, there's also, so this is everything that's in operation, but then there's also these emissions which are already embodied into that building, and that's from the production of cement and steel. So, and if you look at this, there's some numbers. It really depends always a little bit on where you find the numbers, but here from the IPCC reports, I found that there's 21% of global greenhouse gas emissions coming from buildings. So sometimes you see 20, 22, 23, but I think the 40 that you just posted, I think was a little bit too high, at least according to my knowledge, but I'm happy to learn your sources for that. And that is split up into these indirect emissions and direct emissions, which are usually right now mostly indirect, because most of the energy produced is offsite of the buildings, but some is already on-site, and then there's the embodied emissions around 18%. Like I said, this is very just on a bigger scale. Of course, this is very diverse. Like it may be different in the United States than in Asia, than in Africa, than in Europe, but this is in general this sort of numbers. Also, this is also something that's very specific to each of the countries, but in general, it's an example of where does the energy go in buildings. Yeah, and this is also, like I said, very, very different, but generally you can say, yeah, making things hot, making things cool. So this is actually where most of the energy goes. Like if you look here, for example, most of the energy goes into space heating and space cooling, and then water heating, and in general, then lighting, cooking, and some other appliances. So this is basically a typical split, but like I said, this is very different. Like for example, space cooling differs a lot between the residential sector and the commercial sector. Like in Germany, for example, the residential sector doesn't have so much space cooling, and in Europe at the moment, this is changing right now. So when you're thinking of adaptation, this is something that differs in the future. But right now, the residential sector doesn't have that. But then in other areas of the world where you have a hotter climate already, their space cooling is already a topic. And then there's, like I said, water heating, so for showering, for example. Then there's lights, cookings, and appliances. And you can kind of see that the trend is that right now, final energy is still pretty constant. It should be decreasing a lot more, right? But why is this? I mean, for example, appliances, lighting, cooking, let's say lighting and appliances, this should be going down much more, but in general, and I mean, devices are getting more efficient and more efficient, like the light bulb is much more efficient, and all the devices, like my computer I'm using right now is much more efficient than the computer I used several years ago. But then there's some sort of rebound effects happening where you just happen to then just have more appliances and more lights, right? Lights are something of a interior design concept now. So this is something that is changing, so that while each of my devices, each of my lights may be more efficient, the sum of them still remains, unfortunately, pretty constant over time. But like, again, this is something that's slightly different for each sector of the world, but in total, this is still the case. If you're then looking at where we are in comparison to the Paris Agreement, you can kind of see, like, I mean, there you see like a constant straight line where you go from 2015 to 2050 if you want to reach net zero. And you can kind of see where we should be. We should be on this line if we don't want to have like a nonlinear process to get there. And at the beginning, this was working okay-ish. And you can kind of see that if you look at 2020, I mean, it in theory looks like we were going back up to this line. But if you then see, know what happened in the world, that in 2020 we had a global pandemic, which meant that we didn't use a lot of office buildings, for example. This just shows that, okay, we saved a lot of energy, but and we were getting closer to the Paris agreements again. But now in 2021, we were actually back to like a trend which is not on that line anymore. So in general, buildings are, yeah, a little bit behind the targets that we should be on. Okay, now we talked a little bit where the emissions are coming from. And now I think it's a good time also for you again to be a little bit thinking about, okay, given that you now know where the emissions are coming from, and what are some effective strategies to mitigate the climate impact of buildings? So here, thinking again, really in general, not with machine learning yet. And I'm handing over to Samuel again.
Thanks, Marcus. I'll wait for a few responses and then share my screen. Okay, here we go.
Retrofitting existing buildings, that's definitely something we need to do, because simply building new buildings is definitely not an option. But if we build new buildings, build green buildings, definitely. Electrification, that's definitely also true. So like I mentioned, currently my building is heated using gas, so that definitely needs to be done. Insulation, replacement of traditional cooling systems, use renewable energy in the buildings. Passive heating and cooling, that's definitely also something. Yeah, that's unfortunately light colors. Okay, that would be interesting what's meant by that. Minimize energy consumption. Use of different green roofs, renewable energy, heat pumps, on-site PV systems, carbon negative materials. Yeah, there's definitely a lot of great answers to that. Yeah, definitely a lot of these strategies are non-digital strategies and also non-AI strategies. So what we definitely, and they are important. So what we're going to focus though on the next part is, let's share again, a little bit on where to work towards where machine learning could fit into this picture. And for that, let's look again into this. And here you see some of these strategies, which you also highlighted, right? Avoiding demand for energy services and efficient lighting appliances equipment. So this is definitely something that needs to be done. And there's definitely a lot of non-AI solutions to do that. Just making more efficient appliances, for example. But then there's new buildings with high energy performance, which will have a high impact, because I don't know if you've, like, I don't have the numbers here right now, but in general, like a new building is much more energy efficient, like some of the state-of-the-art buildings than buildings that have been built 50, 100, or even more years ago. For example, the building I live in here right now is from around 1900. It has very old windows, high ceilings, and has it's very expensive to heat that in a traditional sense. So that's why new buildings are definitely one part of the solutions, but of course, destroying this building, taking all the embodied emissions that are already here would also be kind of stupid, right? So you kind of have to, what you've also read, improve the existing building stock. So there needs to be something like changing some of the windows, for example, which has been done here, or just putting up insulation, or something like, if you think about digital solutions, what I did is some intelligent heating control, which at least avoids that the apartment is heated at times where I'm not here, or me and my partner are not here. And so all of these strategies are definitely needed. And where does now maybe machine learning come into this play? This is what we're going to talk about in the next slides. So it all boils somehow to intelligent building control, because, I mean, this can help to avoid demand for energy services. As we will see, it can increase the building's energy performance. If you think in primary energy, this works for both new and existing buildings. And of course, what we need to do is increase the use of renewable energies, both on site, if we have like a solar panel here, or like a wind turbine, as we've seen in this figure at the beginning of this image, but also, of course, of the offsite that's generated somewhere, like in my case, close to Berlin in Germany. Some of the wind that maybe if nobody else is using it right now, that maybe if I have something that I can shift to this time, like charging my electric vehicle or something, which I don't have, but if I had it, or I mean, potentially even run my dishwasher or my washing machines at time
where otherwise I'm not a big fan of thinking too much about these household appliances, but at least, running your heat pump, which is a big consumer, or charging your electric vehicle, which is a big consumer at different times, or if you're like thinking of commercial buildings or thinking of industry, then definitely shifting this into times where you have a lot of renewables definitely makes sense. And where does machine learning fit into that? This is where we talk a little bit about building control, or what's also called grid interactive buildings today. Just to motivate this a little bit, and I'm not going to talk too much about it because I mean there's going to be a whole day for AI for the energy system where some of this will be talked about as well. But in general, the energy system is changing, and you now have a lot of let's maybe take you now have a lot of things happening also close to buildings, right? So you now have electric vehicles close to buildings, or you may have something like solar panels, or here you have the electric vehicle connected to the building. Maybe you have even something like a local area grid where you have battery storage or something like this. Now, this is something which wasn't the case 10, 20 years ago. And now in Germany, there's actually this word sector coupling. I think it's not so popular in other parts of but where you see that these different sectors, like the electric energy, the heating, the transportation, they're all coupled now in a way. They're connected. And this gives now the opportunity for buildings to be a more active part, right? Instead of being a passive consumer, which buildings have been most of the times in the past decades, like they just consumed energy, they consumed heating, they consumed electric energy, to being active, connected parts of the energy system. And this means they can, for example, as we will see, shift energy consumptions to renewables. But this also means that, that you can be like a flexibility to the overall electric energy system. So this is actually a term that the Department of Energy in the United States termed the grid interactive efficient buildings. So this is buildings that are energy efficient, that use smart technologies, that have on-site, so this means distributed energy resources, provide demand flexibility while co-optimizing for different objectives like energy costs, and but also, of course, still being a building, being something where occupants live and are comfortable. And they have their preferences, and all this should be optimized for. And this is now where you kind of see where we're going with that, right? So you're going to see that there's now optimization problems that you can solve. And optimization problems can definitely also be solved using machine learning. And what does it mean to provide flexibility? So there's different strategies, and this is sometimes also referred to as demand-side management. So you can imagine now that we have the system where buildings are electrified, where everything is electrified, the transport sector is electrified, the heating is electrified. And now suddenly the grids that typically are planned over many decades. So typically you have planning periods. If you have to decide, you try to put a cable in a way that it works for 50 years. And now with this trend of fast electrification, suddenly your power grids may be not capable to handle these changing patterns. And they may not be able to handle solar production on this lower parts of the grid. And so this means that maybe some of these loads, as you will also see in the energy lecture, need to be changed. So this means, for example, that you just at peak load times shed some of the loads. And this is something that buildings could also be doing in the future. That, for example, if you have electric vehicles, if you have consumers that you don't necessarily need, like the washing machine, if you have your heating and cooling, which you can, which is okay if it's just 1 Kelvin less, you can shed some of the load. Or you shift some of the load. For example, if you can avoid heating here because it's still warm enough, and then you just heat a little bit later, then you can actually shift some of that energy. Because often, as you will see, thermal processes are a lot slower than these electric processes. So this is actually something that in a paper we tried to take basically to the max, basically by seeing, okay, when you have a building and you feel your walls, I mean, now it's summer in the Northern Hemisphere, but if in the winter you feel your walls and you haven't been to your building for several weeks because you've been on vacation or something, you will feel that the walls, depending on the material of the walls, are pretty cold. But if you've been heating for a couple of days or weeks, they're pretty warm. So they actually can function as a storage, right? Because like, even if like, I mean, like I said, it's hard to say that for me now in summer, but if I turn down my heating, it will not immediately be cold, but first the room temperature will get slowly colder and colder and colder. And then eventually some of the energy stored in the walls will also be emitted still for a while. And only after several days, the building will be completely cold. And so since we've seen that now all these different sectors are coupled in a way, for example, with heat pumps or power to heat, you can now use a building also basically as a flexibility, as almost like a battery for the power system. So this is what we did in this building, where we then used generalized additive models. You could debate if this is machine learning or not, but it's a regression model where we used parts of that model to model all the non-linear effects of how the thermal processes, and to then have like a linear control, which we can use in linear optimization models. And in simulation studies, we could see that the building could basically function like a battery. So here in the middle, you see what it would look like with a battery. You can kind of see, okay, so there's different parts where it would discharge and charge. And instead of a battery now, you see that the building is actually then fulfilling this role, basically being a flexibility to the power grid. And you could imagine that this could maybe save the need for a battery in a certain case. But this is just to show where this goes with buildings. Of course, beyond all this shifting energy, also saving energy is needed. So this is basically what's shown here. I mean, doesn't mean that the curve needs to be shifted exactly like this, but in general, I think, I mean, the area under this curve should be getting smaller and smaller. Then what you've also had in your answers, there needs to be decentral production of energy. So buildings should have solar panels, like here, for example. You see that, okay, buildings that have solar power now have a load profile like this, where you basically have the normal power production, the power consumption that you would usually have, plus your solar production. And there's even times when you're now, instead of consuming energy, producing energy. And then you could even shift some of your load because maybe you don't want to be producing energy. And then you could actually go to a load profile, which is more looking like this, where you're now taking some of the energy which you would usually maybe produce, put it into times to flatten your load profile. So this would be an ideal where you could go. But of course, like, I mean, some of these measures to get there are more efficient, are more cost efficient, and some of these measures are more expensive. So definitely this is like maybe a little bit of an ideal image, but just to show where it goes. And as you can imagine now that, and as we will see in a second, that in order to get there, you need advanced forecasting and optimization techniques to really properly do this. Because, I mean, suddenly you have solar generation. You have to decide when is the optimal point to run your battery. You have to decide when to run your power to heat. You have to decide, like, you have to look to the outside, basically. You have to see, okay, what are other people in Germany are doing? What is the electricity prices? And these all these different factors you have to now take into your optimization. And this requires you to at least do something intelligent. To really understand that, let's maybe also see how it is done right now. For that, let's look at some example building. Here we have some commercial building. And we are now getting there that modern buildings, you also have this information about your HVAC system. You have information maybe about your rooftop solar, about your charging stations. You may be able
This is also something which is not state of the art everywhere, but you may be able to control some of your electric vehicle charging. You may have a battery storage. As we've seen in the paper that I worked on, you have thermal mass of the building that you can work with. You know, maybe, for example, what parts of the buildings are used when. This could be simply by occupancy sensing. This could be by having access to the calendars. You may have some loads that you can control, some lights that you can control. And all of this information you can now look at in a computer and decide, okay, what's the best thing to do. And the current state of the art in most buildings is something that's called reactive control. So you basically have simple rules where you say, okay, the outside temperature is less than 4 degrees. It's 12 noon on a working day. So this may be the point of time where, I don't know, we close the blinds because this is typically where the sun is shining into this part of the building. And that's why we're closing these blinds. And, or this, I don't know, it may be at night, so we can shut down all the lights or stuff like that. So this is a very simple reactive control. I mean, what you see here is even like a little bit more advanced already. So if you're like an engineer, you definitely know this. So this is aiming at modeling something that's called PID control. So basically you have a controller and you have some process that is controlled by this controller, and then you have disturbances which affect the process. So basically what it means, for example, you want to heat a room, you have some desired temperature that you want to reach, let's say 20 degrees. The output decides, okay, what needs to be done to get to these 20 degrees. So this could be setting like a thermostat to a certain number. Then you see what happens. I mean, you have sun shining, you have the outside temperature, you have something happening with the building. So this is what's called the disturbances. And then in the end, you can observe what's happening. And you may be not exactly at 20 degrees, but at 19.5 degrees. So this is what you would then measure, get this information back to your controller. And then you're in this sort of control loop where you're always trying to get towards this 20 degrees. So sometimes you're a little bit above that. So you may change your thermostat and so on. So this is the basic, I mean, this is very well researched and simulated and for decades now. And this is a pretty standard thing. And this is what happens right now in most of the buildings. But that means if you want to look at prices that are going to come in over the next of the days or the next hours, solar production in Germany, or you want to look at, or you even want to do something like deciding when is the best time to run a battery or charge the cars, because you know that people don't need their cars until they end working, for example, then this may not be optimal, right? Because this is not really looking into the future. It's only looking what is currently happening and trying to getting closer to that. So that's why and we don't go deep, but there's a great paper by Jan, who's also a core team member at Climate Change AI, that has written a great introductory paper to that, which is called All You Need to Know About Model Predictive Control. There's something that's called model predictive control. That's one of the methods you can use to control a building, more advanced, right? And there you basically, the main difference is that you're actually looking into the future. So you're now modeling these disturbances as well, which in this case means the weather, which in this case means, for example, yeah, you have some sort of model of the building. And this is basically this. And then you have an optimization problem that you can solve and go then into this loop and doing this a little bit more intelligently. And this is now requiring you to have models of your building. This is now requiring you to have forecasts of what's going to happen in the next hours. And this is, as we will see in the next remaining hour, I guess, where machine learning can, of course, come in. We will also see that beyond model predictive control, you can directly optimize buildings also using, for example, reinforcement learning. But model predictive control is also a term you're going to see more and more in the next slides.
Okay, there's a good point now also if there's direct questions to the understanding that you could maybe ask right now, because in the next section, we're going to go into machine learning applications in this area. But if up to now you have some questions, you could maybe ask this right now. And secondly, I would also, so far we focused, and most of the lecture will be about this, we focused on how buildings affect climate change. But what I want to ask you is now briefly, how does climate change affect buildings and maybe cities? So maybe you can fill out this form again with a short answer. And if there are questions for your understanding, you could also ask that right now.
Thanks, Marcus. So there are some questions coming in. I will go through some of them. So some questions. Here's one. Is the split of energy consumption in building referring to Europe?
Yeah, I would have to look up this. I mean, I'm going to share these slides at the end. So I think this was, yeah, I wanted to look it up because I know that I was stumbling across this. So it's referring to this. Yeah, I would have to look up the source.
Paper, the IC,
I think it's internationally. Yeah.
Okay, cool. Another question: how can AI-enabled smart buildings help optimize energy consumption and reduce energy waste in high-rise buildings and cities?
Yeah, I mean the machine learning part will be the next section. So let's maybe keep this question to.
Sure. Okay, here's a nice one on the intelligent control that you just presented. Are intelligent control systems vulnerable to various types of cyber attacks due to their high requirements of communication networks to convey, sense, and control data?
I have to say this is not really my expertise in this area, but I mean, like my intuition would be yes, because I mean, typically, like if you have just a regular control building, using like the sort of more simpler controls, you don't need to connect your building controller to the internet. You can be completely basically having a energy management system, and even if you connect it to weather services or so, you don't have so many requirements to connection. And the buildings then I worked in, this was usually then a local area network, not connected to the internet. But of course, if you're opening this up to more sources, and it's maybe even like a building that sends their data to specific markets, for example, then yes, I mean, you have more communication channels, and in general, I would say this opens the potential for attacks, yes. But of course, like I can also speak again for Germany here, but in Germany, like the whole, everything around this communication out of, let's say, it's called the smart meter gateway, for example, is heavily regulated. So in theory, it should, of course, the risk should be minimized, but yeah, of course, they are not zero.
Great, thanks. I'm going to share the poll results here for the question.
Yeah. Changing, yeah. Okay, the extreme weather makes building climate control more difficult. Yeah, that could be the case. Destroys the strengths of building materials. Yeah. Rain, yeah. Natural disasters, definitely. Increasing the cooling need. That's definitely also one that I was aiming for. Yeah, natural disasters. So all very good answers. Erosion, corrosion, definitely. Yeah, ventilation. Yeah, good. That's also very good answers. Let's go to what I prepared. So there's actually like a section also on that again in the IPCC reports. Again, here I just looked at the technical summary report. But yeah, buildings and adaptation. Yeah, I mean, basically what you were aiming at. I mean, I'm not focusing so much on this part in this lecture today, but just for the complete picture, I wanted to include it. Yeah, I mean, what you said, I mean, there's sea level rise, there's floods, which in many cities of the world causes many problems, which causes maybe relocations or upgrades of the buildings, or you have to come up with some sort of dams around the building or whatever. But yeah, also what we've seen, cooling needs. This is definitely something which on the building level makes sense, right? Like last year when I gave this lecture, I was standing here sweating because it was so hot in Berlin, which in Berlin is not normal. Usually after 2 or 3 days, you have a rain and then it's cooling down again. So this is actually what's happening this summer. But last year it was hot for several weeks. And this is something where German buildings are just not made for. Like you can't cool down in the night, and you don't have like a AC unit or something. And so that's why definitely this is something where in the future, if this happens more and more, I may need to update the cooling of the building, because otherwise it's definitely going to be a health issue, right? Like in Germany, we're then talking about, for example, we have hospitals which don't have cooling, which in other parts of the world is normal, but in Germany, usually it wasn't the case, but now it is. And then if you're thinking on the city level, so I was just visiting a workshop on this last week, then you're talking about, okay, how can we design cities in a way to have better health of the people, for example, by having more trees or having more green around the city. Okay, but let's, so this was more very general right now, but I want to, of course, go into machine learning now. And I mean, of course, we were aiming at some general themes already, but let's deep dive a little bit. And you're going to deep dive even more within the tutorials of this lecture. To structure the discussion, I want to use this overview of the Tackling Climate Change with Machine Learning paper that you were introduced also in the first lecture. And so here's several applications that are mentioned. So let's look at the first one, and this is actually one which we basically already talked about a little bit, but it's all about modeling the building's energy. So what do I mean by that? Well, this can be something as simple as forecasting energy loads, because we already said, okay, in order to do a proper model predictive control, I mean, there's the predictive part already in there. We also need to know what's the load of the building. Then, of course, there's also supply of, for example, renewable energy. In this case here, I wrote a paper where we looked at electrical household loads, but of course, you may need also electrical complete building loads, or you need forecasts of the thermal load of the building and so on. And only if you have this sort of information, then you can make these sort of optimizations that we already talked about. But you're gonna actually learn more about forecasting energy loads in the tutorial. Then there's a second problem that I wanted to focus on here, which is called non-intrusive load monitoring. So this is actually not so much about the understanding what's going to happening right now or in the next hours. So it's more one theme that you're going to see with buildings is you want to understand the building load, let's say for a year. You want to understand, why is my energy consumption this year this, and the next year this, and how has it changed over the years? Of course, there's a lot of, let's say, classic analytics that's not doesn't need machine learning, which you can do in Excel or whatever. And this is actually also what happens, right? I mean, this is energy consulting services, for example. But what you can also do is something that's called non-intrusive load monitoring, and where you take your smart meter signal and you take a disaggregation algorithm and try to understand, when is the air conditioner running, when is the fridge running. So this is actually also something that you're going to see in the other tutorial that I'm going to show you in a second. But just one thing that I want to mention here, for both of these problems, there has been a lot of research already been done. So if you want to go into these areas, make sure you're not just writing yet another applying machine learning to these problems, because especially non-intrusive load monitoring, I feel there have been a lot of PhDs written about that. But in practical applications, I've seen startups trying this, and in the residential sector, I've never really seen so great successes with that. I think it's used a little bit in industry and in commercial settings, but sometimes I feel like also with load forecasting, I mean, there's already a lot of research out there, so really do your state of the art properly and like kind of see where you fit in there. Just as I would say that for both of these problems. But if you want to get started with this, there's the non-intrusive load monitoring toolkit, which is great for Python. And this is where you can plug in your favorite machine learning model algorithms. But like I said, this is what you're going to see also in the tutorials that are coming out with this lecture today. So there's a tutorial that I prepared, built on, which is on load forecasting with machine learning. So there I'm going to show you basically how you use machine learning for time series forecasting in this context, how you do the feature modeling, how you evaluate your models. And if you have questions about that, we can meet on July 7th in the office hours. Maybe we can step through some parts of the tutorial together, depending on how many people show up. Then there's the Ask Me Anything next week. But I want to also advertise the other tutorial, because when it's about modeling building energy with machine learning, I'm a big fan of this tutorial on smart meter data that has been submitted to the iClear earlier this year. And yeah, it's also part of that summer school. So they also have office hours this week and the Ask Me Anything this year. Ask Me Anything this week. And here they're doing a lot of things. I mean, I wouldn't even call it a tutorial. It's more like a toolbox even to get you started on these sort of topics. So they show you how to visualize smart meter data, so energy data from smart meters. How to do typical pre-processing, how to do the non-intrusive load monitoring that I just showed you, how to estimate the flexibility using machine learning, how to do anomaly detection, and how to do customer segmentation. So this is a lot of really cool stuff. Like, I don't know, it would have saved me a lot of hours if I had that as a PhD student, where I worked on a lot of this myself, actually. So it's really cool. So if you're working on this area, you want to work on this area, definitely check out this tutorial. So this is really like the forecasting and the understanding energy building data. And now we want to talk about basically what we also did a little bit in the introduction, smart buildings optimization. Because we've already seen, so model predictive control is one way of doing it. And you can use forecasts that I've just shown you to inform these optimization algorithms. But as you will see in the tutorial, the other tutorial actually, in the third tutorial that I want to highlight, reinforcement learning to optimize building energy management systems. Or you can do something which has been done in this paper here by Javier, who did the lecture last year with me. You can also combine reinforcement learning and model predictive control. And if you're interested in that, check out this paper. But here, I just want to give it as an example, because I'm not going to go so much into reinforcement learning here, because the tutorial does a really good job on that. And as we've already seen in the smart meter tutorial, there's also anomaly detection, fault detection, which I would also call fit into here, basically optimizing the building operations by detecting if there's any faults or errors in the systems. This is actually something which I find interesting, because when I was talking to a building operator several years ago, he was saying, hey, this is basically where you have a lot of low-hanging fruits, because every heating system he goes to and he sees in a building, there's definitely a lot of inefficiencies just by these systems, typically, like especially if they're like older systems, because they're typically not perfectly controlled, they're not perfectly parameterized, and so that's why a lot of heating systems are running quite inefficiently, and it's not even detected. So he was saying, if you just have a few sensors and you compare, for example, buildings, you could detect these sort of anomalies. Like I said, I don't want to talk so much about reinforcement learning here, because we have a whole lecture on that, a whole tutorial on that.
So here we have the CityLearn tutorial, which uses reinforcement learning in the CityLearn environment, which is basically like a gym, which you can use to train your reinforcement learning agents. And it also explains you a little bit about reinforcement learning. And the office hours are also this week, and the Ask Me Anything next week. Then you're going to learn about also what this duck has to do with buildings. So this is a duck that's drawn by Kingsley. That's really awesome. So that's why check it out. Also, what's really cool, so this CityLearn framework has been used in the CityLearn challenge at last year's NeurIPS. And there was like a big challenge where you could also win money. And there's going to be one possibly this year again. But what the authors of the tutorial did is they opened again the leaderboard. So you can, if you want, within the summer school, try this tutorial and you tune your agent a little bit and want to submit the results to see how you would have done back in that challenge. This is a great option, but I'm pretty sure Kingsley will talk about that later in his tutorial. And then there's a bonus. Last year in our summer school, we also had building control with reinforcement learning using a different framework, Bob test, which is also really great. It also gives you a great introduction to reinforcement learning. And it's actually, both of these have some similarities, but both of these have also some different approaches to it. So if you're really interested in that, definitely check out both of these. And you can even see the talk from last year still. Okay. So far we focused a lot on the operation of buildings. So we focused a lot on this shorter time scale of optimizing what's going to happen in the next seconds, minutes, hours, or days. But if you think about cities as a whole and you want to optimize the energy consumption of the city as a whole, often what you need is good data of the city, of the energy consumption at the city level, at the district level of part of the cities and so on, to maybe gain some insights into urban planning. And depending on who you are or where in the world you are, you may have good or bad data to do this. For example, if you want to offer consulting services on solar panels, for example, you typically don't have good access to free open source data in a lot of cities. I mean, in some cities there is, but not in others. So let's say you want to, for example, know how high a building is or what the energy consumption of a building is. You typically don't have a lot of information. So here's a paper by Nicola. He's also a core team member of Climate Change AI, and he's going to give the transport lecture. But here is an example from a paper where he uses the height information from buildings, which he got for some cities, because some cities, they use LiDAR data to estimate this height. And he uses this satellite images and OpenStreetMap images and this ground truth height for some of the buildings that he has it for, to then train a model to predict the heights, and also then from that, the energy consumption of the buildings based on some of the features of the buildings. So this is something that you can then use in urban planning, where you don't have the information. Let's say if you have it for part of the city and you want to do the sort of modeling for other parts of the city, or if you have a similar city and it may generalize to that city because it's similar building types of the similar period, you can do this sort of modeling. Kind of similar or slightly different, or like a different approach that I found interesting, where I didn't find a real paper, but I just saw it on Twitter. That's why I wanted to include it. This is where you can use, for example, but because it's a theme that you see every once in a while in papers, also is using, for example, segmentation models to detect buildings. This is actually, I think, what Microsoft does in Bing Maps now also, where they try to use segmentation models to detect the buildings. You could imagine cases for example, you want to offer solar panels again, or you want to calculate the solar potential, then you may want to fine tune this even and just find these parts of the roofs and so on. And then you can scale, for example, estimations of what's the solar potential for certain parts of the city, or so on. Okay, so this is the whole gathering infrastructure data. Yeah, so we modeled now the building's energy for one building. And the thing is that buildings, like we already seen also now with the infrastructure data, buildings are often kind of similar in certain areas of the world, right? So in Berlin, if you have data from several buildings here in the street, many buildings are from the same period, they are similar height. And so some of these features, like your controller, for example, may transfer to other buildings. And so this is definitely also, again, where machine learning can come into play by, for example, training a model on one data set and then transferring part of the knowledge to another building. So here, for example, you see a paper that works with the transfer learning for smart buildings. This is also something that I wrote about in a book, where there are different strategies, especially if you're working with forecasting models also. For example, in traditional statistical modeling, you would typically have one forecasting model per building. So let's say you have one building and you do your training, then you fit your model on your specific your building's historic data to then make predictions in the future. But now if you want to use machine learning models, you can also learn one model on several buildings, and your building may be in there or not, and then do like forecasts for new buildings also, because like I said, many features are transferable. So if you have like thousands of buildings, you can learn your deep learning model or like your machine learning model, and then make predictions also for new buildings. The problem with this is that at some point it's deteriorating, so it's not getting any better. It's my experience also using some of the deep learning models. So typically that's why you may also try some strategies in between. For example, one approach that you often see, and that's called pooling, is you first cluster the data, and then you train one model per cluster to then make predictions for specific buildings. Or you may do something more along these sort of lines, where you have like a global pre-trained model, which you trained on a lot of buildings, take that model to make then predictions for your specific building. And if you have some data, you can fine-tune your model on that specific data. And then, of course, there's different hybrid strategies that you could come up with. Regarding coordination between sectors, I'm not going to talk so much anymore because, yeah, in the introduction of that lecture, I already talked about how the energy consumption of the building, the transport of, sector around the building, if you have charging infrastructure, and the heating of the building are all coming together now within the building. So, like I mentioned already before, there's now, new optimization problems that you can focus on. Good. Now I want to focus on one topic that's not buildings, but it's more cities. And there is now also this theme of, okay, there's now sensing within cities, or the concept of smart cities. And there I want to talk about one project that I'm currently working on. The project is Quantify Trees. So now it's not about buildings, but it's about the trees within the cities. And the problem we have within this project is that in Berlin, the city trees sometimes have been planted several decades ago, and new species are now planted, of course, still. But the problem is that, as I mentioned before, Berlin is getting hotter and hotter now. Many of the tree species which have been growing without problems in the past decades are now not growing very well. And that's why many of the trees have to be irrigated. And currently this is done very manually, basically, for example, with rules like every tree needs to be watered 250 liters or 300 liters. But then we have at the same time now in the changing climate, the problem that water is getting a scarcer resource in the area of Berlin. So that's why if you can save some water in this process while still having trees which are doing fine, then this would be really nice. And here we wanted to see if we can use machine learning to aid the greenery departments. And what we're doing is we have several sensors now with some of the trees. If we had it with all of the trees, this would be quite inefficient and would be quite unsustainable, because then you would have a lot of sensors and they fail and they have to be exchanged and so on. So what we want to do is we have only sensors for some of the trees and then use data about the trees, about the weather, about the shading around the tree and the watering of the tree. And want to fit a machine learning model that can generalize from some of the trees that we're measuring to other trees. And here we are using open data, which in Berlin we have about every tree. We know what tree it is, how old it is, how high it is, what's the general health information about the tree. Also, we know from the greenery departments when it was watered. And also there's a project where citizens of Berlin can, when they water the tree, they can put it into a database. And then we get all this information together with something that we did with the three-dimensional model of Berlin. We calculated the shading of each of the trees. Here you see an example where, for example, this tree is getting a lot of sun and this tree is in the shade. So this affects the watering requirements. Yeah, we fit this into a random forest, or also we tried gradient boosting, but in any case, we just using tree models to make predictions about trees. We kind of like this irony a little bit. I mean, you don't need a more complex model than this because it's tabular data to then get like a forecast or a nowcast, we call it. So nowcast means we get a prediction for all the trees that we don't have sensors for, and a forecast for all of the trees we're predicting. What will it be like in the next 2 weeks, for example? And then also the greenery departments get this dashboard, and here they can try out, okay, what would happen if I water the trees in a week? They can try out what happens if they water 200 liters. They can try out what happens if they water 300 liters. Also, we have an app for the Berlin citizens where people, unfortunately, it's only in German, but where people can actually look at the state of their trees. So if you're in Berlin in the next weeks, just write me a message and I can give you access to that app and you can check out the trees. Okay, so this is what you can do, for example, with sensor data and in the context of a changing climate also, for example. Okay, so this was the overview from the Tackling Climate Change with Machine Learning paper. I really like that. If you want to have a slightly different view on that, there's another preprint that I want to recommend. It's by Harry and some other authors. Harry is also with Climate Change AI. That's why all the building experts are with Climate Change AI, I guess. And here you see some slightly different view, but a lot of the common themes that we already talked about, right? So you have control strategies, either in between buildings or within a building. You have your focus on the occupant. You have something like load prediction, demand response, building control, fault diagnosis, occupancy detections, all the sort of themes that we already talked about. Demand response, cost optimization. So it goes into each of these topics also in detail. So you may also check out this survey paper. Okay, now I wanted to give you some more ideas if you want to go and work on buildings where you could work on. Of course, you can work on forecasting, you can work on reinforcement learning, but just some of the themes I wanted to give you that I'm seeing here. And actually some of these themes you're going to see across the summer school, right? So for example, the next topic, hybrid physical and data-driven modeling. There's something which you've seen already in the lecture on climate science. This is something which you may see in some of the other lectures as well. For example, in the power systems lecture. So the idea here is that when you want to, for example, do model predictive control, or you want to do a simulation of parts of the system, what you can do is you can work purely data-driven with black box models, right? So you take, for example, all the measurements of smart meters and train your model and learn, okay, in certain parts of the day, in certain situations, your building is behaving in this way. Or on the other side, you have white box models. So this is models where you model all the physics of the building. So you model, for example, okay, what's the sort of walls that the building has? You model the time of the day, you model the irradiation, and then you model how the building behaves, because I mean, it's all physics, right? It's all the thermal dynamics that, I mean, there's formulas for that, you can simulate that. And it may be very inefficient to do that for a large building, but you can theoretically still do that. I mean, you can possibly not do it for a whole city on to a certain degree of detail, but for certain buildings, you can put in a lot of detail. But then for reality, you often don't have all that data. So that's why you make simplifications, which, for example, by only modeling representative zones of a building, which means that if you have actual data available, you may get better accuracy using black box models. But then on the other side, if you don't have a lot of data, you may be better with a white box model, because you know physics, and you may get the information for your specific building, and you don't need to train a model. And it may be more reliable because, let's say, a neural network comes up with some prediction which defies physics because it doesn't know physics, then this may happen. So that's why, I mean, there's a lot of research happening to find the perfect mix of these two approaches, to find models where you have real measurements that are data-driven, and where you have some knowledge about physics, which you incorporate in those models. This is something which you've seen in the lecture by Kasia. Here's, for example, some work by Javier, or some work by Jan, which does this. So if you're interested, check out these papers. I'm not a big expert on those, but yeah, I mean, this is the sort of theme I wanted to point you at. Something similar, we talked about reinforcement learning, we talked about model predictive control, we talked about classic PID control. And each of these, like classic control theory and machine learning, have certain positives and negatives, right? So control theory needs less data, because if you only react, you don't need so much data. You have better constraint handling, because again, you know physics, you know, you may include it in your model. It may be more robust, but then on the other hand, machine learning may be cheaper, because I mean, you don't need a big model of your building, for example. And again, this is something where you can then come up with different ways of combining the pros and cons of all of these algorithms, right? So there is something by Jan, for example, the approximate model predictive control, or something like reinforcement learning combined with for building control. Again, different ways of combining reinforcement learning with NPCs and so on. So this is something where you could definitely do some research on, because this balancing these pros and cons of these different methods is very relevant. Then we've already talked a little bit about that when thinking of buildings, there's different time scales. I mean, because they are now connected to the power sector, where sometimes you have to react in milliseconds and seconds and minutes. And then there's thermal comfort, where I said, hey, if I turn down my heating, it's going to stay warm for several minutes, if not hours. And then there's now seasonal variations of, let's say, solar power of a day, but there's also seasonal variations over the year, because on the northern hemisphere in summer you have a lot of solar energy, but not in the winter. And now suddenly you also have the time scale of a whole year, where you may have to shift some of the energy. And coming up with optimization strategies to do this across these different time scales, on the second scale, to the minute and hour scale, to the month scale, this is something which is quite challenging to come up with good models. So this is definitely something you could also check out. Okay, I think we're pretty good in time. Maybe, so if you're really interested in reinforcement learning, I want to highlight also this blog post that is done on the Climate Change AI blog. It's done by Sultan and Kingsley. And they wrote this blog post about a paper they wrote together with a bunch of co-authors, where they looked on certain challenges for reinforcement learning. And this is something where definitely, if you're interested in that, should also check that out, because it may have also some problems that you could be working on. The first challenge is related to if you want to start from scratch with a new building, you may only have a little bit of measurements, how to do this cold start problem, basically. Then from reality, like in a simulator, you always assume you have all the data available all the time. But once you go into a real building or like a real campus or something, you suddenly notice that there are certain delays. For example, smart meter data may only be available every 15 minutes. Or here at the campus in Schöneberg, we use the protocol that is called Modbus, and it's a protocol that's also pretty slow. It sometimes takes several seconds for like a round trip to go. And then if suddenly something goes wrong, you may have to start this round trip again. And only after a few seconds, you typically have all the information available. So it's not really real time, and you have to wait for that. And how to deal this within reality, this is something where there's also research needed, or maybe some practical experience, actually. Then if you're familiar with reinforcement learning, you know that it's difficult if you have a lot of different states, if you have continuous variables, and this is typically the case. If you're working in the energy system, you typically, like let's say the state of charge of your battery, the temperature within your rooms. This can get tricky quite a bit, because typically you have a lot of values that you have to look at. So that's why it's high dimensional, and typically they are continuous. And so you may reach a very large action space pretty fast. So there's something which you could be working on. Yeah, we already talked about system constraints, some of them coming from the comfort of users, some of them from physics. So this is something you could also be thinking about, how to incorporate this into your machine learning models. Yeah, and also in reality, I mean, similar to the trees, it's not worth to put sensors everywhere. Like in a building, you typically have some sensors somewhere, like the smart meter that's connecting you to the outside of the building. But then you don't want to have sensors in every room of your building, in every zone of your building. Typically, you only have it at certain relevant points. So that's why you have a system that is only partially observable. And so this is also something where you could do research in how many sensors do you really need. And then use something like non-intrusive load monitoring, for example, to think about what's happening in the non-observed parts. We already heard there's a lot of different objective functions that you could optimize for, be it, of course, I mean, a building should fulfill comfort to some extent, but typically there's also some flexibility, because you don't need, I mean, you don't feel differences of, let's say, half a degree Kelvin or half a Kelvin. And but then there's also maybe prices. There may be CO2 emissions locally. There's CO2 emissions of the whole city or the power grid, and all these different objective functions are somehow related. And yeah, training offline. So coming up with strategies. So this is also related to the first question, I guess. So yeah, coming up with policies that you don't have to try out with the real building, because I mean, if you always try out your actions and get feedback, oh, this is too hot, this is too cold, this is too hot, this is too cold, you really don't want to do this too much with your inhabitants. So that's why coming up with some sort of offline training where you don't need the real environment definitely is really important. And also something that I noticed, I mean, I already told you at the beginning that most building operations right now are simply rule-based. And this is how it has been for several years now. And a system operator, like a building operator, and you're going to come and tell them, hey, I have this cool model predictive control algorithm, I have this cool reinforcement learning algorithm. They're not going to trust it if they don't really understand what's happening. So that's why coming up with explanations for reinforcement learning, but also for the other approaches is definitely something which will have a higher impact and make it more trustable and get these sort of algorithms faster into the real world. Okay, that's good because my voice is getting a little bit quiet now, but think a little bit more freely again. This is more like not meant to be an exercise where I have the perfect answer for you, but I just thought, hey, everybody's talking about large language models, foundational models, generative AI. So maybe answer in your Google form. If you have any ideas, I mean, now you learned about buildings, you learned about more classical AI, reinforcement learning, supervised learning, a little bit of unsupervised learning, but maybe you have any ideas of how large language models or generative AI could fit into this picture.
Great, thanks, Marcus. Also, we have some questions that are built up. Marcus, do you want to jump into them now or take them at the end?
Sure, I think now it's a good point.
Yeah, okay. So while we wait for the poll, let me pull up some of these questions. So Marcus, you said a lot of PhDs have been written in the area. I think this was referring to when you were talking.
I think load forecasting and non-intrusive load monitoring. Yeah.
What do you see as the main challenge that needs to be bridged from PhD research to practical implementation?
I'm happy, like I don't have the answer, to be honest. I mean, there's also a great blog post by Stephen Haben on our climate change AI blog, which is called Bridging the Gap, which looked especially for the energy sector, and they came up with some common themes. But like I really at this point towards the end of my, when I was working as a researcher, where I was like talking to DSOs, I was talking to building operators, and they're really not aware of all these thousands of papers that I probably looked at in my time as a PhD researcher. And this kind of gave me like an existential crisis also, because I was like, why is so many smart people working on load forecasting? And I mean, I wrote a survey paper, which I think I linked also on the slide, where we also critiqued very specific things, because I think especially in load forecasting, they don't do a really good job in benchmarking their approaches to each other. So people are coming up with their big machine learning model, and they don't really compare it well to many of the others, simpler state of the art, for example. So typically, for example, you have a machine learning person that comes up with this CNN and LSTM, compares these, but they don't compare to some good statistical benchmark, to some good basic benchmark. They only compare to some naive model maybe, which is then also not hard to beat. And so you kind of see a lot of these patterns where I think the research itself is also not so great, but then this jump into practice, I was also, I don't know the perfect answer, to be honest. I mean, a lot of the discussions I had were along the lines that they're simply having other problems at the beginning right now, and load forecasts weren't so important to them at this time. But I think this is changing now. So load forecasts are getting more and more important. And I think, so on the higher system levels, machine learning is applied already. So I think machine learning will be applied also now in the building sector more and more. But let's say 2 years ago, when I was talking to a lot of people, it was still more simple models, more seasonal models. Because people, I don't know, maybe it was not their biggest concern at this time.
Wait, here's one interesting question on biophilic design. Biophilic design of buildings is being promoted these days. However, they suffer from challenges of limited space, budget, and maintenance, which requires architects to be creative with their designs. How can AI models be used to create designs of such biophilic architecture? Not sure if that's an area of your.
Yeah, like I have to say, this is really not something I know. I mean, I know there's often constraints in reality. So I can also just give an anecdote of a project where we wanted to have back then it was a CHP of a specific size, and it was just not possible to fit it into that space. So this was like a real world constraint, which I don't know. When we did our optimization, our simulation, and we said, hey, we want to have this size, but then in reality, it just didn't fit in because like CHPs, they cause noise, they cause vibrations, and like a larger one just didn't fit in. So, but I think, I don't know if machine learning would have helped there. Like,
sure. Okay, here's one on the trees, the trees project, I think you showed us. So how to select trees for AI for hotter cities based on climate conditions?
Yeah, there's some research on that. So this is not buildings now, but trees. So I know, like, yeah, I mean, they're trying this out, and they're trying different types of trees. And what we hope to do in this project also is look into some of these influencing factors. Right now, we are focusing also on these operational challenges to decide when to water the trees. But at the end of the project, it will end this year. We also try to see if in the data we can find out, okay, I mean, we right now only have the shading and so on and the watering, but we want to see if we can model using some, for example, explainability, AI explainable, XAI methods to understand really what are the influencing factors for the irrigation requirements. And something similar we hope to do maybe in the future with maybe also if there's like a master student or something who's interested in that, or a PhD student, reach out to us because we also have ideas to combine this with microclimate and heat index data and so on, and to really understand if we can come up with some understanding of that we can then talk to the greenery departments with. Right now, our greenery departments, they're doing this a lot by feeling. I mean, they are gardeners and they're very experienced, and they do this right now by trial and error. But I know there's also some chairs in Germany at least working on that. I'm not totally aware of internationally, but here, yeah. TU Dresden, for example.
Great, thank you. And I'll do one last one. This is a nice one on AI. So is it possible to reset a PID system for a building with AI? Say, for example, if the AI is incorrect, what are some of the feedback mechanisms for these models, online or offline?
I'm also not an expert so much on these control methods. But in general, like, I mean, this goes into this, what I had in my last slides also, right? I mean, there's different ways of how these traditional control algorithms can be combined with machine learning. So I'm pretty certain, like for the specific question, I can't answer that. I mean, you could reach out to me and I can connect you some of the authors in the slides that are working on this. But in general, yeah, machine learning can be combined with PID controllers.
Great, thank you. I'm going to jump to the poll now. Let's see some of the answers here.
Prediction, yeah, may not fit. It's purely physics. Alexa and Home Assistants. Yeah, so basically telling your smart building about your constraints. Sending notifications. Analyze building blueprints. That would be interesting how. Oh yeah, right. I mean, they can understanding. Yeah, that's definitely the case, because at the beginning when we talked to system operators, they often still had very unstructured blueprints. So I could imagine there's now good language image models that can maybe make this more structured.
Mhm.
Predictive maintenance. Okay, that would be interesting. Yeah, conversational agents. Yeah, sounds good. Also good ideas. I mean, I can only, like I said, this was more like a, just to maybe you guys have ideas. Maybe one idea that I came up with in the context of urban planning is I think like using these image models. I mean, this is DALL-E, and I did this several months ago, so you can possibly do it a lot better now. But I think one cool idea that I always like is that you can make things very personal with these sort of models. So what I did here is basically it's an image down my street. And you can come up with different versions of your street, right? So what I did here is basically see, okay, how would climate impacts affect my street if there was a flood? Or this, I mean, this is very dystopian, but I kind of like to have also more utopian kind of futures of my street to kind of think about, hey, what would be if there's no cars and just people walking? So I actually talk to cities now about this sort of ideas, and some cities are trying out something like this, maybe using augmented reality or virtual reality, where you could basically interact with your neighborhood and see how different urban planning measures would affect your street. For example, if you take away a car lane or if you add a car lane, and then you could come up with these sort of simulations, which may or may not use generative AI. A different one that I didn't take in because I didn't find a good image or product to link. But I've seen something along those lines is basically using language model also in energy consulting services. Basically, in many areas of the world, if you want to put a solar panel on your roof, or if you want to put a charging station next to your building, there's a lot of regulatory bodies that you have to be aware of. After, like if your solar panel is 10 square meters, it's different than if it's 20 square meters. Or if you have a solar panel and an electric vehicle charging station, you may have different regulatory bodies. And it's very complicated. And I think language models could be good at understanding these sort of regulatory bodies and also help you in this very first consulting, like if you have that idea. I've seen just prototypes into that direction, but I think this could also be pretty cool. Maybe, yeah, if you're thinking generative AI, there's again one work that I also did with a student where we used normalizing flows, but I'm pretty sure also some sort of transformer models could also be used for that, or the fusion models, I mean. And yeah, you can basically, what we did is we modeled on the one hand side densities, which can be used for some sort of optimization problems, but we also can sample from this multivariate distribution that we learned. And you can kind of see that you have these realistic peaks and shapes, and this could be used, for example, in simulations. This could be used in, for example, stochastic optimization problems. Yeah, or there's other works also by other authors. I think they also used the flow-based model, but there's also GANs in the history, in the literature and so on, that have done something similar. And these sort of models can be used, like I said, for like planning problems, for and often because you often have very related time series. For example, if you had from a building the time series of your EV charging, of your building load, thermal and electric, they're all dependent, right? Because you're typically coming home, plugging in your vehicle, and it starts charging, you go home, your apartment may be heated already, you're suddenly using electric energy because you're cooking and so on. And modeling all these sort of interdependencies, it's not images, it's not text, so it's not as hard, but you have quite nice, very connected time series problems where you could use these sort of models also to model that. Unfortunately, you need very good data sets for that, and there are not so many open data sets that you could possibly use right now. But I'll give you some pointers at the end of this lecture. Okay, and this is actually where we're getting close to. Again, there's the tutorials in the summer school. I really want to, cannot recommend it enough. Like the reinforcement learning lecture, like this is really cool. Also the tutorial on smart metadata, this is also really cool.
basically does everything with smart meter data except forecasting. And for the forecasting, you have my tutorial. They're all pretty cool. Use also the reinforcement learning tutorial from last year. It's also pretty cool if you're really interested in it. Then a shameless plug, some information I already had in there. So if you're really interested in load forecasting, there's this free open access book that I was co-authoring. So I'm going into describing basically how from simple ANN, random forests, decision trees, temporal CNN, LSTMs, and GRUs, how they could be used also for time series. Of course, there's also statistical models in there, some benchmark models, and it describes basically how to compare models, how to evaluate models, and so on. So if you're into load forecasting, energy forecasting, time series forecasting in general, this could be of interest for you. Some other resources, there's the survey that I think also linked into earlier. It's a good start. And there's the wiki, the Tackling Climate Change with Machine Learning paper, the Bob test and the CityLearn framework that I already mentioned, and where we have the tutorials. There's COPS and ACTB, which are similar, always with a slightly different focus approaches, where you can also compare your own control strategies in building simulators. And then for data sets to start, there's, depending on your focus, if you have a long-term focus or if you have a short-term focus, there's different data sets. There's also one list that I'm hosting myself on low voltage load forecasting.github.io. So if you know data sets that I'm missing, I think I have 70 to 80 there now. Also, you can put your own pull requests in there, or let me know and I can put it in there. There's also more. There has been some Kaggle data sets and some more. I mean, this is not exhaustive here, but some data sets if you want to do some work yourself. Some concluding thoughts that I want to finish with, because it's also fueled basically by my own experience. I think if you remember from David's lecture at the beginning of the summer school, machine learning is not a silver bullet. It's only relevant sometimes, and typically only if so as part of an overall strategy. So if you're going into optimizing buildings, basically, machine learning is typically like there. It's especially true. I mean, it's typically not the lowest hanging fruit, right? Like, I mean, your building should have like a certain level of insulation. Otherwise, it's really hard. I mean, the building should have like a solar panel maybe or at some point. Otherwise, you can't do all these cool optimizations of deciding of when to charge your car, when to wash your washing machine. And also here in buildings, like I think I hinted at it also every once in a while, sophisticated algorithms are not always required, right? I mean, often it's time series. So make sure before you try your fancy transformer something model, please try out also some statistical models, have really good benchmarks, have these, and then try to go into like the more fancy, sophisticated algorithm, and really make sure that when you write a paper in this area, that you show that it's really necessary to go that complex. And this is typically only if you have very high resolution data. This is typically if you have data of several buildings. But if you just have, for example, one household, 15-minute resolution, it's really, really hard to fit some good deep learning model on that. And typically some simpler model will be typically the best. Like, I mean, if you then compared also all the effort you had to put in to make it not overfit, then definitely this is the case. Also, and this is what I want to finish with, sometimes like the low-hanging fruit is just Excel and getting the right people together. Maybe here a case study of a product that I was of a project I was involved in with Birds on Mars. We were asked by a mobility and automotive company. Unfortunately, I can't name it right now, but there's going to be a talk about this project pretty soon. So they noticed that after COVID, the occupancy was still pretty low, so it went down really, really low, and it hasn't really gone up to where it was before COVID. But the heating consumption wasn't going down in the same sort of
fashion, because even though like the people were really spread out in this building. So what we did at the beginning was, hey, let's use machine learning, AI, whatever, to help them. But in the end, we realized that AI and machine learning was not always the low-hanging fruit, right? I mean, one initial idea was basically, hey, why not sit together, people close in the building, and then try to find some sort of optimal mix of where people sit, because they have flexible desks. And then we thought, okay, even this could be still a nice optimization problem. And let's do this using optimization methods. But talking to more and more people, you then suddenly have organizational constraints, because suddenly you have people that can't or don't want to move, because it may be upper management. It may be people that need some offline files that they can't move around as we thought they should. Then there's technical constraints. We learned that parts of the building can only be controlled independently. Like, for example, you can only control this part of the building, also with this part of the building, or something like that. So there were different technical constraints, which also made this technical problem really simple at the beginning, because there was basically only this half, or only this part and this part. And also in this case, it was like looking at the money behind it also. I mean, this was already quite efficient. So the absolute savings are pretty low. For example, we found, while it was relatively 10 to 12.5% that we could save by relocating people, in the end, it was not enough money, basically, for the upper management to say, this is worth all the hassle. So in the end, they went for something, because it was last winter, when in Europe, it was all about saving energy really, really fast because of the war. And that they said, okay, let's just lower the temperature by 1 Kelvin, and everybody has to deal with it. And that's saved more energy with what they found, a measure that was for them more easy to do. But we found also quick wins, for example, because there's other buildings around this building, and we found, okay, there's the canteen, and if we close that, we can save 2 to 2.5%. If we close it on Fridays, for example, and they go to the neighboring buildings, because the canteen is using a lot of energy. And this was one of the quick wins we found. But again, this was just Excel talking to people, and not really AI and machine learning. So in the end, this is just some final words that I wanted to give with you. Remember, there's a lot of cool problems, and you can work on these cool machine learning and optimization problems, but keep in mind to also talk to people out there and what the real problems are. And I hope this gave you some inspiration. Yeah, thanks.
Thanks very much, Marcus. That was a fantastic seminar. We didn't seem to have any more further questions after we took the previous set. But thanks also. I did take a look at your book. It's really, really good read. I think I strongly encourage people to check that out and continue to engage on the platform for other discussions. And let me just quickly see if there's other questions here coming through. And if not, I think we can. Danlin, did we have anything? Maybe we can maybe wrap up.
Yeah, there's one more question. The participant is curious, what are the most energy-less problems to load forecasting? Do methods used in safe forecasting work?
So, sorry, what was it like in load forecasting?
Yeah, load forecast.
Analogous problems to load forecasting. For instance, do sale forecasting methods work when you're forecasting sales? I guess that's what they're trying to ask here.
Okay. I mean, but what we noticed that, I mean, the load forecasting as it is phrased right now is often you have like a smart meter signal in 15-minute resolution, and you're basically trying to model that. And typically what you find is that because it's the expected value, it's often like not modeling like the true peaks, for example, of a load profile, especially if you're like on a building level, household level, you often have these sort of peaks which may occur. But if you have this expected value, you're kind of smoothing through these sort of peaks, because sometimes you don't know if it's like within this 15-minute interval or this 15-minute interval. So what we found, some system operators or grid operators are sometimes interested in, is not really the sort of expected load profile, but more also what's the highest peak in a certain area, or what's the highest, like the highest expected peak, for example, at certain times, because then they can match this with peaks in the area, or match this with peaks. So, for example, peak forecasting is definitely something that one could look at. But in general, I think also just probabilistic forecasting in this area is still quite interesting, because then you can compare basically, because I mean, solar forecasting is also very hard, because like, I mean, solar predictions beyond certain, like a few hours, I guess, it's hard. I mean, there's going to be large errors anyhow. So that's why having probabilistic forecasts for solar forecasts, and then also having probabilistic forecasts of your building load, and then maybe coming up with some sort of stochastic robust optimization or these sort of methods, and using stochastic forecasts as an input. I think the sort of directions make really sense, because, like I said, I mean, like especially in the household or small building, you have these sort of peaks where you're going to be wrong anyhow, because you're just having the expected value. And similar for solar panels. I mean, if there's like clouds coming over, you may have the dip here, or you may have it half an hour later. And having this, modeling this sort of problems probabilistically, I think this is quite interesting and can be of value.
Thank you.
Yeah. Thank you. And I think the students, they are more interested into the tree model forecasting. Yeah, and one question is as this forecasting, while time series related methods like RNN model, long short-term model transformers evaluated as tree models, they are not known for capturing transient behavior of the data.
Yeah, in this case, with the specific tree data set, the problems that we are working on daily aggregation. So we're having, like, even though we have several measurements per day, typically they're not changing so much. We are currently aggregating it to a daily level. So we have a daily time series, which means for one tree, you may have per year 365, or maybe sometimes we have 2 years of data. But you don't have so many data points, even though you have a lot of trees. But even, I mean, we only have sensors at like around 200 trees right now. So this is not a lot of data. So if you try to fit LSTM, screw or something to time series data, then you know that this is not a lot of data to work with. So that's why we focused on simpler methods. And I mean, you can do, and you're going to see this in the load forecasting tutorial, you can model some of the like what happened the days before, what happened, like the autoregressive features. You can model like a taking like a moving average over the last several days and the sort of features. And this, for this difficulty of problem, is definitely enough, and it's not really worth investing much more time into more complex models, but instead right now we figure it's more worth trying new features, like, for example, adding a new data source. For example, what we don't have so much in the model is the data of the ground, for example, because it's very difficult in cities to know what's happening underground, because there's like the water system, there's the electricity system, and they all do their stuff, and nobody really knows how the ground is looking like in underground in Berlin. Like, there's no single source of data that you have, and then there's different soil next to each of the trees, and you don't really, I mean, they don't sample soil everywhere in Berlin, and this may be even within a certain location be very diverse, because I mean parts of Berlin have been destroyed in the war. So at some area there may still be some of the material from back then below the ground. In other areas there's new soil and so on. So it's very difficult. And so we're rather thinking, okay, maybe let's include some of this data, or let's include. So for example, we know also from talking to the experts that the facades next to the trees are also playing a big impact, because like we know, for example, if there's a lot of glass, the sun may also be mirrored towards the trees and so on. So we thinking about new data sources, and for example, solar data, or this facade data, soil data, groundwater data, and so on, is currently worth more than trying much more complex models. So this is where that's why we haven't tried some fancy transformer models or something.
Thank you.
This is typically also true for buildings, right? I mean, like for time series, really start simple, and then do your homework with a good statistical model, and maybe some good tabular model, and then going towards more fancy models.
Great. So I think with that we can now conclude today's excellent session by Marcus on AI buildings and cities. Marcus, thank you so much for your time for this very insightful lecture on the different aspects of AI in buildings and cities. Thank you, Danlin. Thank you, Climate Change AI, Eric, for all the support and pulling this together. Have a great day and rest of your week.
Thank you, and maybe see you in the tutorial.
Great. Thank you. Bye-bye.
Thank you.